Hello, future insurance subscribers, viewers, and students. Here is another final video on cables, this time subjected to varying load. So we use the concept on the general cable theorem here because the load to varying is projected upon the horizontal. So the cable shown supports the linearly varying load. The tangent at A is horizontal. So determine the equation of the cable, the maximum tension in the cable, the maximum distance of the point of the cable to the imaginary cord, D sub n or D sub max, and the total length of the cable. So this is the free body diagram. Take note, it is mentioned that the tangent at A is horizontal. So the tension is just H. The horizontal component of tension is the same because the loading is projected upon the horizontal. Therefore, the area of this loading, which is 1/2 of 30 meters times 90, is 1350 kilonewtons. That should also be the vertical component of tension at B. The maximum tension in the cable occurs at B, so we need to solve for H. To solve for H, we sum up moments about B equals 0, so H times 8 equals 1350, and this distance is 10 meters, which is 1/3 of 30. So equals 1350 times 10. H therefore is 1687.5 kilonewtons. So the maximum tension can now be computed, but I defer it first. So I want to determine the equation of the cable first. So let's follow the statement here that we should first find the equation of the cable. To do that, let's apply the general cable theorem. That is the product of the horizontal component of tension and the distance from the point on the cable to the imaginary cord, which is D, is equal to the moment at the same point on the cable loaded with same loading. So this is the beam and the loading is the same, triangular, then we have 90 kilonewtons per meter. So let's solve for the reaction at the left end. Summation of moments about the right end equals 0. Remember, the equivalent loading of this triangular load is a point load of 1350 kilonewtons located 10 meters from the right or 20 meters from the left. So summation of moment about the right side equals 0. So reaction at the left support times 30 equals 1350 times 10. So solving for the reaction at the left, it is equal to 450 kilonewtons. I just mentioned it so that those who want to understand the solution will carefully listen to the discussion. And I intentionally do it so that uh, you will learn by listening, or you may solve it by your own. Then summation moments about the left equals 0. 900 times 30 equals 1350 times 20. So you'll get 900 kilonewtons. That's why 450 plus 900 is 1350 kilonewtons. So since we want to compute the moment in general at a section, so this is the shear force also. So take note that the shear equation is just summation forces y, considering this portion of the free body diagram. So shear is equal to 450 minus the area of this triangular load, 1/2 of x times W, where W in general is by similar triangles, W as 2x equals 90 as to 30, so W is 3x. So the shear equation up to that section is equal to 450 minus 1/2 of x times W, which is 3x. We then equate it to 0 to locate 0 shear, which corresponds to maximum moment. So x therefore is 10 square root of 3 meters. That's the distance from the left end where moment is maximum, so that we can compute also this maximum sag, d sub n, or d sub max. So the maximum moment is the moment at that section with x 10 square root of 3. So it is 450 times x, which is 10 square root of 3, minus 1/2 of x is 10 square root of 3, times w, which is 3x, 3 times 10 square root of 3, times moment arm x over 3. So 10 square root of 3 over 3. Cancel 3. So moment is 450 times 10 square root of 3 minus 1/2 of quantity 10 square root of 3 cube. And that is 5,196.152 kilonewton meter. The maximum sag, therefore, which occurs at the point where moment is maximum at x equals 10 square root of 3 meters, is by principle on the general cable theorem, the product of the horizontal component of tension and d sub n is equal to the maximum moment, or the moment at the same point. D sub m therefore is 3.079 meters, and we'll solve this again after we define the equation of the cable. Let's now define the equation of the cable by the definition by the general cable theorem, that is H, which is 1687.5, times sag, which is this distance. This distance is the slope of this imaginary chord is 8 over 30, or 4 over 15. In general, at a distance x, the vertical distance of that point on the chord, imaginary chord, to the x-axis is slope 4 over 15. Again, 8 over 30 is 4 over 15 times x, so it is denoted here. And this distance is y from the x-axis to the point on the cable. Therefore, the sag in general is 4 over 15 of x minus y. So h times sag in general 4 over 15x minus y is equal to the moment at the same point on the beam. And that moment is 450 times x minus 1/2 of x times w, which is 3x, moment arm x over 3. Simplifying, 1687.5 times 4x over 15 is 450x minus 1687.5 times y equals 450x minus x cubed over 2. So we cancel 450x, divide everything by negative 1687.5. So the equation of the cable is y equals x cubed over 375. It is x cubed or cubic because the load is first degree. The expected equation of the cable is degree of the load plus 2. So that's why it's third degree. So that's the equation of the cable, and we can check that when x is 0, y is 0. When x is 30, 30 cubed over 375, you will get y is 8 meters. So let's now compute the maximum tension, because that's the second question. Tmax is square root of, although we can compute this earlier, h square, which is 1687.5 square, plus the vertical component of tension 1350 square. So the maximum tension is 2161 kilonewtons. The slope at B is 1350 over h 1687.5, you will notice that it is 4/5. And to verify that the slope is 4/5 at D, when x is 30, you derive y prime here. So y prime is 3x squared over 3375, and that is x squared over 1125. So when x is 30, 30 squared over 1125, you will notice that it is 4/5. So the angle at B is inverse tangent of 4/5, and that's 38.66 degrees. Another way of computing the tension is it is equal to h divided by cosine of the angle theta B. So 1687.5 h divided by cosine of 38.66 degrees, and it will give us 2161 kilonewtons. Again, the slope of 4/5 is from y prime equals x squared over 1125, and you substitute x is 30. And inverse tangent of 4/5 is 38.66 degrees. That's theta B. So T max is also h over cosine of 38.66. You get that. So another way of computing d sub n is it is 4/5 of x, and x is 10 square root of 3 where moment is maximum. So 4 over 15 of x, 4 over 15 of 10 square root of 3 minus y, and y is from the equation of the curve x cubed, so 10 square root of 3 cubed over 3,375. You will get the same answer of 3.079 meters. And another important concept or for you to explore is that the tangent at the point on the cable where sag is maximum is parallel to the imaginary chord, or the slope at the where point on the cable where sag is maximum is parallel to the slope of or parallel to the chord joining the supports. Since the slope of the chord joining the supports is 8 over 30 or 4 over 15, you will notice that when x is 10 square root of 3 at the point where moment is maximum, square into this slope here over 1125 is also 4 over 15. Although this is not part, I just want you to explore this because that's the principle, and I already presented this in the preceding examples, and it is still true. So the length of the cable is square root of 1 plus y prime square dx, and limit 0 to 30, and the approximate length of cable is square root of 30 square plus 8 square. That's the straight line distance for the length of AB, but the length of the cable is longer. So it is 31.78 meters with your calculator. So that's it for this video.